Let me just say, I mean, before people got in here, Adam was asking about. Um, I was just talking to him about the last lecture, which was on the exponential distribution. And before that, we had looked at the uniform distribution carefully. And he noticed that the CDF, the cumulative distribution function, was so nice for those two, right? He had a really nice cumulative distribution function for the exponential, and then we had a pretty nice one for the uniform. And he was saying, hey, why don't we have like nice formulas for the cumulative distribution functions in the discrete cases? You know, like the binomial and the Poisson distribution. And the answer to that question is uh, that that it doesn't exist. There isn't a nice form. You just have to add all of them together. That's it. And that's why I moved you immediately toward doing those problems in Excel. So hopefully that makes sense. So you just utilizing Excel does the job. It turns out that the Poisson, you know, you can factor out like the e to the minus lambda, and so that makes that one a little bit nicer to work with. The binomial is just a mess because you have all those chooses in it, like, you know, in choose 0 and choose 1, etc. That just gets really, really bad. So using technology is the way to go. It used to be that every book had a giant table in the back that just told you various sums up to certain points for various binomial distributions. But in here, we talked about using the Poisson to approximate the binomial, right? Didn't we do that in here?
I think so.
Yeah, that we can like say lambda is equal to n times p, and we can like actually approximate using the Poisson distribution, the binomial. The reason you would want to do that is because the Poisson's just easier to work with. That's it. Okay, Poisson's easier to work with the binomial, but it's still a mess. If you want to add a bunch of them together, you have to resort to using technology. Okay. All right. So please ask a question. Anybody? Anybody have anything?
Can you explain more how the Poisson and exponential are related to each other?
So, okay. So sorry, you're kind of muffled a little bit there, Anthony. Was that Anthony?
Yeah.
Okay. Say again.
Explain how the Poisson and the exponential are related to each other again.
Yeah. Yeah. Here, give me a sec. I'll get into. Let me get into the meeting here with my iPad, and I'll do that. There I am. Okay, here it comes. Hey, page 100. How awesome is that? Okay. So let's see here. 100 pages of math. How exciting. So how are the Poisson and the exponential related to each other? So, I mean, suppose you're observing, you know, something. This is like an interval. This is like an interval of time. This is like an interval of time or something, right? And suppose you expect to see, so we expect like lambda observations observations over this interval. So in other words, if x is equal to the number of observations on this interval, then the expected value of x, right, which we often notate by mu, that's just lambda. Okay, and we know that the PDF you know, the probability distribution function, probability mass function, which by the way is the probability that x is equal to little x. What was the formula for this? Does anybody remember? What was the formula for this? Oh, by the way, this is called, this right here is distributed as the Poisson, right? Distributed as the Poisson with parameter lambda. Does anybody remember what the probability of being equal to little x was? I'll give you a hint. There's e to the minus lambda, but there's some other stuff. E to the minus lambda times.
Lambda to the x over
Yeah,
factorial.
lambda to the x over x factorial. And that's for, right, x could be 0, 1, 2, could be any non-negative integer, okay? Okay, so if I define, okay, so like if I define y equal to the first, so let me, not the first, y is equal to the time to the first observation, okay? Okay, so that is, you know, if I have an observation here, right, a car goes by here, if there's another observation right here, if there's another one right here, right, and there's another one up here in this thing, then then y would be this amount of time right here that passed until the first observation. Does that make sense? It's the amount of time until the first observation. And y is going to have the exponential distribution with parameter lambda. Okay? Y is going to have the exponential distribution with parameter lambda. And of course, you know, the density f of, let me use little y. F of little y is going to be lambda e to the minus lambda y. And this is for y greater than or equal to 0. And it's 0 otherwise. And the cumulative distribution function for this thing is just 1 minus e to the minus lambda y for y greater than or equal to 0. Okay? So y is simply the amount of time that passes until the first observation occurs in this Poisson process. Okay? And I mean, so if lambda was like equal to 2 or something, let me go to a new page right here. If lambda was like equal to 2, okay, so that means like in our interval, we expect to see, just expect how many observations? How many observations do we expect to see? We expect 2 observations in there, okay? And suppose that this was like, this is like 1 hour or something like that. Okay, then you know, x distributed as Poisson with parameter lambda, y is distributed as, right, and so here we go. You know, maybe this is an observation right here. The amount of time that passes to that first observation is what we call y. Y has the exponential distribution with parameter lambda. What do you expect, right? What is the expected amount of time, do you think? If I expect to see 2, if I expect to see 2 over that 1 hour, how long do you expect to have to wait to see the first one? If I'm going to see 2 in 1 hour, how long do I expect to have to wait to see the first one?
Half an hour.
Yeah, half an hour, right? Which is, by the way, just 1 over lambda, okay? And that's why the 1 over lambda kind of makes sense as like the expected amount of time. Now, I didn't like go into the details as to why, you know, why this is the density, why this is the cumulative distribution function, but it's actually not that hard to explain. It just comes from working with this thing, working with the actual probability mass function for the Poisson. So it's probably not worth our while to go into a ton of detail beyond what's written here, but that's the basic connection between the Poisson distribution and the exponential. Okay, the exponential is simply the amount of time passes to the first observation in a Poisson process. That's the main thing I want you to get out of all of this. Does that kind of make sense? Was that you, Anthony, that asked about that?
Yeah, that answered my question. Thank you.
Yeah. Okay. What else? Any other questions?
Why is the exponential distribution the same shape as exponential decay when it's not necessarily getting smaller the whole time?
Well, okay. So Madeline, right. So let me just kind of, let me go over here to the next page. Okay. So what does the graph of f of y equal to lambda e to the minus lambda y for y greater than or equal to 0? What does that look like? Well, it looks like this. Okay. If I were to graph that thing, remember lambda is positive, so it makes sense that this thing would be right, because look, I mean, lambda is just some positive number, so e to the minus this thing, doesn't it make sense that it would just be going down like that, Madeline?
Yeah, that makes much more sense.
And this is lambda right here, where it crosses the vertical axis is lambda. Incidentally, I mean, this is kind of confusing. I'm using y on the x-axis right now, and this is, this is f of y. I'm graphing y versus f of y. But that's why this thing is decaying like that. And what does this mean? Remember, we get probabilities. Like if I wanted the probability that y was between two numbers, these two numbers right here, I would have to integrate this function, right? Right, the probability that a is less than y is less than b would be the integral from a to b of f of y dy. Okay, I would have to integrate that thing. So this tells us that we're going to get higher probabilities. Where, Madeline? Where are we going to get higher probabilities?
After b.
Well, okay, so like if I were to shift this interval from a to b around, where am I going to get higher probabilities? Close to 0 or far away from 0? Just based on this picture, where is the area going to be biggest? If I were to like shift this thing around.
Like going from like b to forever, how long it goes.
Right. So okay, here. Let me just put some actual numbers in here. Like maybe 1 to 2 or something like that. Okay. How would that compare, Madeline, with say, another interval of length 1? Maybe I go down here and I go to like 1/2, right? From 0.5 to like, 1.5 or something. How would this, all right? And so that blue stuff, that would represent the probability that 0.5 is less than y is less than 1.5. Still an interval of width 1, but how would the probability compare to the probability of being between 1 and 2? Would it be big?
Yeah, it's bigger because
it's bigger. So this
is like higher.
Yeah, right. So it goes up higher. So this would be bigger than the probability that 1 is less than y is less than 2. And what if I went out here? What if I went to like, between 4 and 5? Okay. What about between like 4 and 5? Where would that lie relative to all these probabilities?
That's just much smaller than everything.
Yeah, right. So right, that thing right there, that would be the probability that 4 is less than y is less than 5. So do you see what's happening? That's why in the slides I was saying, the lower values are more likely to occur. Does that make sense?
Yeah, that makes a lot of sense.
Yeah.
Thank
So
you.
the reason you have exponential decay is because the density is just a decaying exponential function. And it kind of makes sense that the longer that, right, so that this thing, you know, it's less likely to keep taking longer and longer as time goes on. It's getting less and less likely to have to like keep waiting. Does that make sense? to observe one of these things. So it does make sense that the probability keeps decreasing the further out you go. Yeah. Hopefully, does that make sense?
Yeah, that makes sense. Thank you.
Okay. What else? What other questions do you have? Anything? So here's the plan. We're done with chapter 4 and 5 in Olowski-Dean. I'm going to do chapter 6. Okay, I'm going to start doing that on Friday. I'll probably finish it on Monday. That's just going to be nothing but concentrating on the normal distribution. It's going to be exclusive focus on that. And then once we have that in our back pocket, we're going to be able to start doing lots of statistical applications. Okay. So I will post this afternoon, I will post some problems to work on from chapter 4 and 5 in Olowski-Dean. Okay, I know you have plenty of stuff to work on right now. You know, you have a test that's supposed to be turned in by 5 p.m. Wasn't that what I said? 5? Did I say 5?
Yeah, it's 5.
Yeah, 5. So yeah, you can make sure you turn that exam in by 5 p.m. Okay, but by this afternoon, I'll post some problems you can be working on from chapter 4 and 5 in Olowski-Dean. It won't be a ton of stuff, but you know, just stuff that you can, you know, fiddle around with for the next week or something like that. You could come in and ask questions about it. And then I'll probably next, you know, probably by, you know, next Wednesday or something, or maybe even a little bit earlier, I'll go ahead and I'll post a homework quiz for you to work on. And I'll you know, usually I like to have about a 48-hour turnaround or something. So maybe I'll post that next Wednesday or something, and then you'll have to turn that in on Friday. Okay. So that's kind of the plan going forward. So I'll post the homework problems from chapter 4 and 5 this afternoon. Hopefully that makes sense. Any other questions?
Yeah, on the Excel, when you were doing the last ones, you made it cumulative. What would happen if it wasn't cumulative, since like the probability of one spot is 0?
Yeah, it would just be 0. Yeah. So you can, you mean like if okay, so like what kind of a question are you thinking that we would be asking then, Anthony?
I'm not sure. I just like when you're doing the exponential distribution, you did like 3 1/5 and 1, and 1 was for cumulative. But like if you don't do cumulative, then what are you calculating? If that is it even a thing?
Oh, all that's giving you, oh, that's a good question. Because the probability is definitely 0 of being equal to that value, right? All that it's giving you is the value of the density. It's giving you the value of the function at that y value. Because like, I mean, for instance, look right here. Can you see my mouse moving around right now?
Yeah.
Okay, so I'm highlighting the density here. If I plug in various,
I can't see it moving. It's still.
oh, well, let me go right here. Let's go with purple. This thing right here. Yeah. If I plug, I can plug numbers into that, right, Anthony?
Yeah.
So so what I'm saying is, when you tell it, when you say, no, I don't want the cumulative, all it's going to give you is the density value. But that's not the probability, right? The density is the thing you integrate to get probabilities, but all it's going to give you is the actual value of the density. So for example, let me okay, let me actually go into Excel and do this. Hey, this is exactly from that thing, right? So here's like the probability that X is less than 4, right? See this? You guys seeing this? And what Anthony is saying is, what if instead I would have said, hey, what did I have? Let me actually pull this. In Excel, you can actually pull things down like that, copy it. So 4 1/5, what, okay, so you're saying to change this 1 right here to a 0. Is that right, Anthony?
Yeah.
And you would think that it would say 0 because the probability of being equal to a number is 0 in a continuous distribution. But it doesn't give me that. What's going on? Okay. Well, what was our so what our lambda was 4 in this one? Is that what that is? Or wait, no, that was the X value, right? Lambda was a 5th. Okay. Watch, I'll show you what it's doing. It's just taking the density. Remember, the density is lambda, which is a 5th, times the exponential function raised to which power? Well, it would be negative X over 5, right? Whatever the X value is over 5. And what was our X value in this case that we were going up to? 4/5, like this, watch. And what do you think this is going to be? I'm telling you, it's going to be exactly the thing that we just computed. Boom. Do you see that these are the same? So all Excel is doing is actually giving you the value of the density function. But that's not a probability. Does that make sense, hopefully?
Yes. Thank you.
Yeah. And by the way, it can't be a probability because, or let me go in here. It can't be a probability because of this. Let me go here. So Madeline had asked about this thing. Okay. Notice what's the leftmost value here in the graph of the density? What's the leftmost value of the density? It's lambda. If you plug in 0, you get lambda. Well, what if lambda was something like 7? Then the density is like up to 7. So that can't possibly be a probability, right? I mean, it's too big of a number to be a probability. But when I integrate this function over an interval, I do get probabilities. Okay, this whole thing, the entire area under this curve, all of the area under there is going to be 1 if I were to integrate the whole thing. Okay, but the values could be higher than 1. That's kind of a confusing situation. The density values oftentimes will be bigger than 1, but still, when you integrate the whole thing, you get something. You get an area of 1. Okay, probabilities correspond to areas, not function values anymore. Does that make sense, Anthony?
Yes. Thank you.
Okay. All right. Anything else? Well, hey, thank you all for coming in here and asking good questions. Appreciate it. I'll post this on YouTube, has been my habit so far, just so you can go back and refer to it if you want. Yeah. Thanks for coming in. Appreciate it.
Thank you.
Yeah.